All right, we are continuing with Unit 10, Infinite Sequences and Series. Today we will look at convergence or divergence for infinite series. So I have to share with you a little funny. We've been home almost a year now, right? This pandemic's been going on for a year. So I was upstairs in the closet where I keep my math things, and I found my notes that I brought home last March. I haven't had any of my notes with me all year, but we've gone a full year. So I have my solutions to help out a little bit. Anyway, just a reflection point there. Kind of crazy. Anyway, a series is a summation of infinite terms. We can't add up an infinite amount, so we look at partial sums. We look at adding them up part way. Now, of course, I was excited that I have my answer key. I just don't happen to have it for this lesson, but that's okay. This doesn't mean much to you right now, but the sign of 1 can actually be approximated by this this list of sums. When you're adding and subtracting things together, you can actually estimate what sign is. Now, this isn't sign of X, but this is the sign of 1. I feel like I should give you a little bit of background information here because this feels very, very random. Hold that thought. We're going to switch over to Desmos and I'm going to show you something. Okay, so we're back. So I have 2 curves for you. The red curve is the sign of X, and this blue curve is X minus X to the 3rd over 3 factorial, et cetera, et cetera, et cetera, kind of what you have in your notes. So if we want to estimate what the sign of 1 is, we would put 1 in for all of those X's. And in fact, the one in your notes goes up a little bit further, it goes to the 11th. So I'm going to do X to the 11th over 11 factorial. Now, obviously there's a pattern here and we will talk about that later. This will come along with Taylor polynomials later. But if I zoom in a little bit, I want you to be able to see what's going on. I can come over here at 1 and the 2 lines, the 2 curves overlap at 1. There we go. The red curve's at 1. So if we want to calculate the sign of 1, yes, we have a calculator to do that, but you can estimate these transcendental functions, sine, cosine, e to the x, natural log of x. You can actually estimate those with just a polynomial. So they're kind of funky, crazy polynomials, and this is what we have here. This is my funky, crazy polynomial. It's called a Taylor polynomial, and I'll show you how to calculate those a little bit later on. But for that first example, I can estimate the sign of 1 when I add or subtract all of these together. So let's go back and see what it looks like. I'm gonna pause this here. Okay, so we have these partial sums. So that's what that capital S is sum. So sum means we're adding, right? And technically adding or subtracting, you're adding positive or negative values. So if you have the sum of 2 terms, that's really 1 minus 1 over 3 factorial. And I'm going to cheat a little bit here. It's in our old textbook. By the way, do you remember what factorial is? Factorial is 3 times 2 times 1. You multiply and you start with the highest value and you go all the way down to 1. So this becomes 0.833. If we add the first 3 terms, you've got 1 minus 1 over 3 factorial plus 1 over 5 factorial. My decimal equivalent, this is approximately 0.841667. If I do 4 terms, I would have 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial. And that is approximately 0.841468. And the sum of 5 terms, 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial plus 1 over 9 factorial is about 0.8414709846. I know we didn't issue you textbooks this year, but that's the textbook that I'm getting all this out of. All right, so those are my estimates for the sign of 1. But what if I just pull out my calculator, making sure I'm in radians, and figure out what the sign of 1 is? Well, the sign of 1 in my calculator is 0.84147409848079. So we are accurate all the way through that 84 to here. To here, the values match. And if I keep adding more terms, the more accurate I would be for actually sine of 1, right? So 5 terms is good, 6 terms would be better, 7 terms would be better, 10 terms would be great, 100 terms would be even better, but I don't want to add and subtract 100 terms. But what would be the best estimate? An infinite number of terms. Remember that infinity we talked about in Unit 1? We're coming full circle for infinity. So you can't add up the infinite amount. So we're going to look at some partial sums. And that's what that little subscript is. It tells you how many sums you have. So I have a couple specific sequences here. If we look at, remember, my series is we take the terms of a sequence and we add them together. So that's the difference between a sequence and a series. I wish the names sounded a little bit more different than they do. But your sequence is the individual terms, and the series is when you add those terms together. So 1/3, 1/9, 1/27. My general term is 1/3 to the n. Hopefully you're starting to be able to see these a little bit. That this would be 1/3 to the first, 1/3 squared, 1/3 to the third, 1/3 to the fourth. And when you put those plus signs in there, that's where you use the sigma. You might see that sigma if you do any spreadsheet work in Excel. The formulas, they do have that sigma in there for sum. Sigma means sum. The next one I have is, same idea, 1/n squared. Those are the individual terms of the sequence, but as soon as I put those plus signs in there, now it's a series. Now it's a series. You can only find the sum of a geometric series. This is a big idea. You can only find the sum of a geometric series. The rest we have to look at convergence versus divergence. And remember, there's a lot of vocabulary here in this unit. Convergence is where we find a number. Doesn't really matter what that number is. And divergence means infinity. By the way, 0 is a number. So if you have a sum that reaches 2, you say that it converges. But we can only find that exact sum for a geometric series. We'll come back to that in a second. I just want to kind of come back here, reiterate your sequence versus your series. Your sequence, these are your terms. You've got some kind of pattern. The sequence are the individual terms. Those generally tend towards 0. They get smaller and smaller and smaller. Often, they don't have to, but a lot of times they get smaller and smaller and smaller. When you have this plus sign in between each of them, you're getting larger and larger and larger. Now, if you add 1/27, you're not adding much value at all. So it's getting larger, but very, very slowly. So just keep in mind the difference between sequence and series. Now, we have a few different kinds of series. The first one I have for you is a telescoping series. It's similar to this format that's here. And I know that your practice problems for today, for this lesson, do have some telescoping series on there. This one's pretty straightforward. I think the ones in your practice lesson have a little bit more going on in them, but let's see what we can figure out here. So my telescoping series, sometimes I find it's helpful to write out some terms. So n is 1, so this would be 1/1 times 2, plus 1/2 times 3, plus 1/3 times 4, plus 1/4 times 5, plus 1/5 times 6. So you can kind of see what's going on here. So I've got 1/2 plus 1/6 plus 1/12 plus 1/20 plus 1/30. And those would continue to get smaller and smaller and smaller. Now, on a side note, I want to find a pattern. I don't want to have to find the first 99 terms in order to find the 100th term. So let's look at this another way. We're going to take a little detour over here. 1/n times n plus 1. When's the last time you saw fractions written like this? Remember doing integrals with partial fractions? So this would be 1 equals a times n plus 1. And here's my b times n. Let's say n is equal to 0. 1 is equal to a times 1. So a is equal to 1. And say n is equal to a negative 1. You have 1 equals 0, b negative 1. So b is equal to negative 1. So why am I doing all of this? Well, I want to show you something. 1 over n minus 1 over n plus 1. So I can turn this expression into this expression through partial fractions. I was always somebody who needed to see it instead of just believing it. So there's your seeing it. Now, if I have the sum of one term, that would be 1 over 1 minus 1 over 1 plus 1. So this is 1 minus 1/2, which is 1/2, which I would get here. That's 1/2. I do have a point to all of this. Bear with me. So this is, if I do two terms, it's 1 minus 1/2. And then the second term would be 1 over 2 minus 1 over 3. And we'll come back to that in a second. Well, be 1/2 plus 1/6. 1/2 plus 1/6 is actually 2/3. If I do three terms, it would be 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. Maybe you can start to see a pattern here. If I add all of those together, by the way, let's use a different color here. This would be 1 minus 1/2. I want to switch those around. New plan. This, nope, I have the 1 minus 1/2. So this is equal to 1/2. This would be 1 minus 1/3, which is equal to 2/3, which I just mentioned. This one is going to be 1 minus 1/4, which is equal to 3/4. What do you suppose one with 4 terms would be? Can you start to see the pattern? It's going to be 1 minus 1/5, which would be 4/5. Well, how are we getting all of that? So let's back up a moment here. A negative 1/2 and a positive 1/2 cancel out. So you're left with 1 minus 1/3. A negative 1/2 and a positive 1/2 cancel out. The negative 1/3 and the positive 1/3 cancel out. So you have 1 minus 1/4. So the same thing's going to happen as you continue on. Now, if we want a formula in general, we could say the sum of any number of terms is 1 minus 1 over n plus 1. And in fact, they used a capital N. And so that fits. If you had 4 terms, it's 1 minus 1/5, that n plus 1. So now you have a formula to find that sum for any number of terms. You don't have to find the first 99 in order to get the 100th. All right, geometric series. You have seen these before in geometry, but I know geometry was 8th or 9th grade for a lot of you, so it was a long time ago. Your geometric series is a ratio that's raised to a power. That's what you're looking for in a geometric series. That's really the hallmark of it. The c in the front is a coefficient. You can multiply it by any value. If that ratio is less than 1, that fraction, we say ratio, but it's a fraction. If that fraction is less than 1, it converges. That sum will converge to a value, and you can actually figure out what that value is. But these are the two formulas. Notice the difference. This series starts at 0. This is your formula. The one on the bottom starts at m. This is your formula. But a lot of times people just memorize the one on the bottom. There's no reason to memorize the special case on the top. You can just put 0 in for m and it would work. You also need to know that if that fraction, that ratio is greater than 1, it will diverge. So what do I mean by all of that? Let me come back here to the first one where it's less than 1. Say we have 1/2. 1/2 plus well, no, 1/2 to the n would be 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. Those values are getting smaller and smaller and smaller. It will converge. If you have a fraction that's larger than 1, say 3/2, we've got 3/2 to the n, this would be 3/2 plus 9/4 plus 27/8. I mean, you're adding numbers larger than 1 each time. So that sum will diverge. It's going to eventually get to infinity. It gets bigger and bigger and bigger. So example 1, let's evaluate 7, -3/4 to the n, where we're going from 3 to infinity here. Okay, so it's a geometric series. You want to be able to start to identify these because we'll have different kinds of series. I know that it's geometric because I have this fraction raised to an exponent. So we know that c is equal to 7. We know that that ratio is a -3/4. So we know that it's geometric because it has this fraction. Now, if the absolute value of r is less than 1, then it will converge. So the absolute value of a -3/4 is 3/4. It is less than 1. This will converge. But what's the sum? Well, the sum is this formula up above, and it starts at 3. So my sum is n equals 3 to infinity, c, which is 7, -3/4 to the n. Here's my sum, c r to the m over 1 minus r. So you just have to put in the pieces. This is 7 and -3/4 to the third over 1 minus a -3/4. Let's do some mental math here. So this is 27, -27, 4 times 4 is 16, 16 times 16. Yikes, I need help with that one. This is going to be 3 7/4. I'm going to put 4 cubed here. I'm going to cheat a little bit. So when we rearrange this, 7 -27 over 4 cubed, multiplied by the reciprocal 4/7. So I know that the 7s cancel out. This 4 cancels with one of those 4. So this is really 4 squared. So now I have -27 over 16. And that's what my solution says. So that's the sum. If you add up those terms, it will converge and you have -27 over 16 as the sum. All right. Test number 1, the divergence test. This is just normal, regular, do the terms converge or diverge? If a sub n does not converge to 0, then the sum diverges. So if a sub n does not converge to 0, then the sum diverges. So in order for that sum to converge to get to a value, even though we don't know what the value is, your terms have to tend towards 0. You have to add up pieces that are smaller and smaller and smaller and smaller and smaller and start to add up to 0. Each term is smaller, closer to 0, and then you can have a full sum. If those terms themselves go to anything other than a 0, then the whole thing is going to diverge. So let's check this out. Does this converge? Well, while we're getting used to things, it's easiest to write out some terms. So if n equals 1, I'm going to do 2, 3, and 4. I have a -1 to the 1 times 1 over 2. My second term would be -1 squared and 2 over 3 and -1 cubed and 3 over 4 and -1 to the 4th and 4 over 5. So this becomes -1/2 plus 2/3 minus 3/4 plus 4/5. So what's going on with each individual term? This is what the sum looks like when we add or subtract. That's my sum. Your individual terms are -1/2, +2/3, -3/4, +4/5. This is your sequence. The question is, are these terms approaching 0? The answer is no, they're not. This is -0.5, +0.6, -0.75, +0.8. Something called alternating, we'll get to that later, but this is tending towards a -1 or a +1. So we would say no, this diverges. Those terms are not getting smaller, they're getting bigger. They tend to -1 and +1. This is a little bit strange, I know that, but just you want to look for that pattern. It has to get to 0. If those terms, remember A sub n is the terms, if those terms converge to 0, then the series may or may not converge. Well, great. You told me if it doesn't go to 0, then it has to diverge. Now I'm saying if it does go to 0, it might converge or might diverge. Yep, we don't know yet. So here is one that's 1 over the square root of n. So again, sometimes it helps to write out the terms. We would have 1 over the square root of 1, and then 1 over the square root of 2, and 1 over the square root of 3, and 1 over the square root of 4, bless you, 1 over the square root of 5, bless you. Those are my terms. Now, each of these are getting smaller because the denominator is getting larger. Each term is getting smaller. So these do indeed tend to 0. What else do I want to say about this one? I think for this one, it's easiest to look at some specific values. So if we do one term, my sum would be 1. 2 terms would be 1 plus 1 over root 2. 3 terms would be 1 plus 1 over root 2 plus 1 over root 3. 4 terms would be 1 over 1 plus root 2 plus 1 over root 3 plus 1 over root 4. Now, I don't have specific calculator values there. I'm going to come right back. So I paused the video and came up with some values. I have the decimal equivalents of each of the terms in our sequence. And then I added them together in a series to get these sums. Now, the sums are definitely going up. They're going up a little bit more slowly. I've gone from 2.2 to 2.7. I don't really want to write that out again. There is a bit of a proof that goes along with this one. So I'm going to try to do my best here. If I come down here and look at sum of 4, right? The sum of n terms would be equal to 1 plus 1 over square root of 2 plus 1 over square root of 3, ... fill in all the pieces to 1 over the square root of n. This value would have to be less than or equal to, now this is the proof part where you kind of make up the other part. So if you can prove one piece, you can show what happens here. So if the other piece, if I just added in 1 over the square root of n, square root of n plus 1 over the square root of n, that represents kind of the first 3, and then we did ... 1 over the square root of n, which is the last one. If we did that for n number of terms, my actual sum, I my inequality backwards. I'm teaching inequalities in Algebra 1 right now, yikes. The real sum would have to be bigger than this estimate. So basically what I'm doing on the right-hand side is I'm taking that last term, the smallest one, whatever it is, and adding it up n number of times. So if I do that, my sum has to be greater than or equal to n. No, this is what happens. get rid of this. Okay, back up. I had the n too soon. If I replace each one of these with 1 over the square root of n, the actual sum itself would be greater than or equal to the sum of adding the smallest term repeatedly. Now I've got it. So if I add all those up, I have n number of terms, so it's 1 over the square root of n. And if you simplify that 1 over the square root of n, this becomes the square root of n. So my sum of n number of terms has to be greater than or equal to the square root of n. What does that have to do with anything? Take the limit as n approaches infinity of the square root of n. If you put infinity in place of this n, you get infinity. So the smallest value, this right-hand side, the smaller value is going to go to infinity. So if that goes to infinity for sum, and the one that's on the other side here, which is bigger, will also have to go to infinity. We're going to do something later called a comparison test. It's kind of what it's leading up towards. So if the smaller one goes to infinity, then the larger one has to go to infinity. But we don't use infinity anymore. We use the word diverges. All right. It's a little bit tough. Mrs. Oakes and I were talking about this, that sometimes it's easier to say converge or diverge, and then that reasoning why can be tricky. I think example 4 will be better, and this is our last example. This is, we want to find the sum. This is actually a geometric series in disguise. You can break this apart. This becomes n equals 0 to infinity, 2 over 5 to the n, plus 3 over 5, and each of these have an n. So what you're allowed to do is make it 2 separate series. So n equals 0 to infinity, 2 over 5 to the n, 0 to infinity, 3 to the n over 5 to the n. So we've broken it into 2 pieces. Now, I feel like the entire series unit is a lesson in exponent rules. This is why we learn exponent rules in Algebra 1, and this is 3/5 to the n. So I think this one's a little bit easier to see on the right, that you can combine those two, numerator and denominator, into one fraction. The first one, I just pulled the 2 to the front, kind of as that c value. And that 1/5, so just pretend there's an invisible 1 here. And 1 to any power is still 1, so you can introduce that n. That's totally allowed. And this is your r, and here's your r. So if we want to use that sum formula that we have before, remember the fraction has to be less than 1, which it is, so these both converge. We can use that formula that we had way back here. You know, we're jumping around a bit. And do these start at 0? These start at 0, so I can use this one. C over 1 minus r. So C over 1 minus r plus C over 1 minus r. So this would be 2 over 4/5 plus 1 over 2/5. This would be 10/4 plus 5/2. 10/4 plus 10/4. 20/4, which is 5. So the sum of that geometric series is 5. So when you add up all of those terms all the way to infinity, you get 5. And I know this seems like an abstract topic that, hey, if you just add more value, then the number gets bigger and bigger and bigger. That's what we tell our younger students, but that's not actually necessarily true. And so the best visual that I have for that is this. If you have a box, and you can look these up online and see them, that's 1 by 1. If you cut it in half, this side is a 1/2. If you cut this side in half, you have a 1/4. And keep cutting it in half. This is a 1/8. Then this is a 1/16. And this is a 1/32. And this is a 1/64. And this is a 1 over 128. And then you keep going smaller and smaller and smaller. Have I changed the area of the box? Have I changed the sum? I have not, but you can still add those fractions. 1/2 plus 1/4 plus 1/8 plus 1/16. that's a series. So this one, the sum of all those fractions, and this would keep going forever and ever and ever because I can make these fractions smaller and smaller, that sum would still be 1. So it takes a little bit of getting used to, but you'll get there. You'll get there.